Okay, we're going to talk about optimization problems for functions of two variables. This is a topic that you most likely did in first quarter calculus. Once you learned how to take the derivative, it's a very common to do a lesson on how to optimize a function of one variable. That's the difference. And now we can have the ability to find max and min values for functions of two variables, so we can tackle some more complicated type problems. Okay, so here's my first one. It's number 31 in our book from 9.6. Find the volume of the largest rectangular box in the first octant. Remember, the first octant is where x, y, and z are all positive, where the three faces are lined up on the coordinate plane. So what that means is the bottom of the box is on the xy plane. Okay. And the back side right here would be on the xz plane, and this back would be on the yz plane. And then the opposite corner is touching the plane, x plus 2y plus 3z equals 6. That would be a plane that has an intercept of 2 on the z-axis, 3 on the y, and 6 on the x-axis. So it looks like a triangle, but remember the plane keeps going in all directions. We're just looking at the portion in the first octant. So our box is actually behind that plane and the far corner is touching it. Okay. And we're looking for the largest box that we could fit here. So obviously you'd want that corner to be, touching the plane. That would be the largest box. Okay, so the volume of our box is just going to be x, y times z, length times width times height. But because that far corner would be touching the equation of the plane, we can actually get this equation. We can solve for z in our equation of our plane, plug that into our volume equation, and now we can get our volume to be a function of just x and y, which is what we are used to dealing with. So I solve for z here, plugged it in, and I've got this. And then I'm going to distribute the x, y to simplify this, because I now know what this becomes now is what we've been doing earlier, finding the critical points of this function. That's where we can find absolute max and mins, or relative max mins. So we're going to take our partial derivatives. V sub x, you should make sure you can get this answer. Take your partial with respect to x. Gives me this. Try V sub y, make sure you get that answer. You can pause the video. For V sub x, I factored out a 2y, and I got 2y times 1 minus 1/3 x minus 1/3 y. Now remember, normally critical points, you would set these both equal to 0. That would give me y equals 0 as a possible critical point. What is nice about an optimization problem is because it has context and y actually stands for a side of the box here, we know if y was 0, you would not get any volume. So we know that can't be the answer, right? We can rule that out. So the only possible answer is coming from this part right here. So what I did, if I set this equal to 0, I just solved it for, put the x and y terms on the other side. Similarly for v sub y, I factored out an x. That gives me x equals 0 is a possibility, but of course that can't work, so we just rule that out. And I have this equation. So what I did, the critical point's going to come from setting this equation and this equation, from solving them simultaneously. What I did to do this was not the only way, but this is the way I saw it. I saw that they both had a 1/3 x. So I solved this equation for 1/3 x by just subtracting the 1/3 y, and I plugged it in here. So I plugged in 1/3 x became 1 minus 1/3 y. And then my equation's all in terms of y. If you solve that, you get y equals 1. Put that back into here, and I can now solve for x, and I got x equals 2. So my one and only critical point is x equals 2, x equals 1. It kind of stands to reason that that's the only critical number. I know there has to be a box that's the biggest volume that I could fit behind that plane. And if I only get one critical point, that has to be the dimensions that give me the maximum volume. Nevertheless, we can confirm that, okay, using the second partials test. We can confirm that 2, 1 gives us a max as opposed to a min or maybe a saddle or something like that. So if you go back and look at it, you should be able to get f sub x, x, negative 2/3 y, f sub y, y is negative 4/3 x, and f sub x, y, 2 minus 2/3 x minus 4/3 y. If you plug in your critical number 2, 1 into your second partials test, you get negative 2/3 times negative 8/3 minus negative 2/3 squared. That gives me 16/9 minus 4/9, which is positive 12/9. If d comes out to be greater than 0, then it's either a max or a min. And so what have we been doing? We've been looking at the signs of f sub x, x and f sub y, y. If d is positive, they'll both have the same sign, guaranteed. And because they're both negative, that tells us our graph is concave down in the x and y direction, which confirms what we already knew, was that our critical point was going to give us a maximum. So our maximum dimensions would be 2 for x, 1 for y. Go back to your z equation and plug that in, x and y in for that. You should get z equals 4/3. Another type of an optimization problem that's very common is finding the closest point or the shortest distance, in this case from the point 2, 1, negative 1 to the plane x plus y minus z equals 1. So the plane has intercepts. I just plotted my intercepts. It actually has a negative z intercept. So it's actually going down below the xy plane. 2, 1, negative 1 is not on our plane. And what we're trying to figure out is what is the shortest distance from that point to that plane. We don't know where that point is, so we're going to call it xyz temporarily. That's hard to read. That's xyz. And we want to minimize the distance. So we're going to use the old distance formula, the square root of x minus 2 plus y minus 1 plus z minus negative 1, which is really z plus 1 squared. Like the last problem, we want to get our equation in just 2 variables. So how do we do that? Well, our point xyz has to lie on this plane, kind of like the last problem, which means z would have to satisfy the equation of the plane. So I took the equation of the plane and just solved it for z. Plug that in. Notice if you plug in x plus y minus 1 and then add 1, the ones will cancel. And my equation now is just in terms of x and y. Now, the next step would be to take the partial derivatives of this to find your critical numbers. You can tell this would be really difficult because of the square root. Taking the derivative is going to be messy. So there's a little trick on this, and if you did this similar type of a problem in a single variable calculus in 17a, you may remember this trick. Is we're going to, it's a safe assumption, I think, but we're going to assume that the minimum value of the square root of all of this junk just depends on what's underneath the square root. So we're just going to find the minimum value of what's underneath the square root, okay, which is x minus 2 squared plus y minus 1 squared plus x plus y squared. And that becomes much simpler, right? You take your first partial derivatives with respect to x and with respect to y. Make sure you can do that. I would maybe pause the video, go through the algebra here, make sure you can get the same critical points I'm going to get. When I took f sub x, I simplified it a little bit, divided by 2. I got an equation of a line. Same thing for f sub y. Simplified that. So you have 2 lines, which means our critical point is going to be the intersection of those 2 lines, the common solution. This time what I did is I just solved one of them. I solved the f sub x for y, plugged it into f sub y, and did some algebra, got x equals 1, put that right back in. That tells me y is 0. again, like the previous problem, we have to agree that there is a closest point, right? From a plane to a point, there is a solution to that, right? There is a closest point. The math we did gave us one critical point. So that has to be our answer. This number has to give us a minimum distance. But we can still confirm that using the second partials test. So we can plug that in. Whoa, here we go. F sub xx, if you go back and look, is 4. F sub yy is 4. F sub xy is 2. And if I run that through the partials, second partials test, I get a positive 12. Both F sub xx and F sub yy are concave up. They're both positive, so I can confirm that that is indeed a minimum. Now, remember the assumption we made where we minimized just what was under the square root. If I actually want to find the minimum distance, which happened when x was 1 and y is 0, I do need to go back to the actual square root equation, right? And plug in 1 for x and 0 for y, and that gives me a minimum distance of the square root of 3. So that's my answer. Okay, one other problem in this section, I guess it's not necessarily an optimization problem, but it's more of a finding the absolute max on a closed boundary. But this one just really caught my attention, and in this current time we're all sheltering in place, trying to contain the spread of this COVID-19 virus. This model seemed particularly poignant to me. So we've talked about this before. It's the R0 model. This particular model, according to the book, was actually developed from data from the SARS virus. This was several years ago. So it's not necessarily true for the model, the true model for what we're looking at right now, but it still gives us an idea of how R0 works. Okay, remember, R0 measures the number of infections caused by an infected individual. V is the vaccination rate, which has to be between 0 and 1, meaning 0 or 100%. And D is the number of days an infectious person is in the population, infecting other people. So now that we know how to find max and mins, kind of a curious question would be, what's the maximum value for R0? Now, we'll make an assumption here, which I think kind of makes sense. What if we would just restrict our model to D being between 0 and 20? Now, why that makes sense to me is that if an infected person is out in the population, probably by 20 days, they've already, assuming they've survived, they have probably already become immune to the disease. Their body has fought it off. So after 20 days, they're not going to be infectious anymore, right? So rather than let D go, pretend D could be infinity, it makes sense to me to only study this for a maximum value of D equals whatever. I don't know how somebody decided on 20, but I could certainly see there would be some, maximum value of D after which everybody's either recovered or not. Okay. So we're going to make those assumptions. Now remember, on a closed boundary, V is also closed, right, between 0 and 1. On a closed boundary, our maximum value can either occur at critical points, corner points, or along the walls, so to speak. Now, so I first looked at my critical points. If you take your partial with respect to D, go back here, that's treating V as a constant and 5 as a constant, so that can just stay there. And if you do a quotient rule, you'll get 1 over 1 plus D squared after you simplify it. Now, the only way this could be 0, this will never equal 0, is if V is equal to 1. If I take my partial with respect to V, holding D as a constant, now this stays there, the 5 stays there, and the derivative of 1 minus V is just negative 1. That will only equal 0 if D is 0. So the one and only critical point I get is 1, 0. But let's analyze this. Let's think about this. What is the value of R0 when D is 0 and V is 1, well, you can plug it into the model and you're going to get 0. Why does that make sense? V equals 1 means 100% of the population is vaccinated against the disease. So they're immune, right? They can't get it. And then furthermore, if D is 0, if anybody happened to get the infection and they stay quarantined, they don't spend any time outside, no, they're not going to spread the disease. So you have both of these working together to give you an R naught value of 0. Of course, that has to be a minimum, right? That's got to be a minimum. We were trying to find the maximum value. So now that we know how this model works, we can kind of shortcut our normal situation. On a normal function, if we don't, previous videos we studied absolute max min points on a closed boundary. We had no idea what the function was really telling us, so we had to investigate everything, right? We had to investigate along the walls and so forth, and all 4 of the corner points. But let's use our intuition now, and I think that's fine in this case. What would maximize R naught? What conditions for V and D would we want? Well, not want, but would be the worst scenario, right? Well, certainly if the vaccination rate was 0, right? And that corresponds to any point along this line. But then what about D? If we take it to the maximum, right? If D was 20, so the average person is out in the population for 20 full days and the vaccination rate is 0, that would produce our maximum R naught. And you just plug it in and you get 100 over 21, which is almost 5, right? And so remember how to think about that. That's saying each individual, right? When R naught reaches 5, that's saying each individual, if I had like, one individual here, is infecting an average of 5 people. Let's call that A, B, C, D, E. And you think each of those 5 people are infecting 5 other people, right? You'd have 5 branches coming off here, each one of those. You can imagine the kind of spread that would do to our disease, right? So an R naught value of 5 is really, really not a good situation, okay? But again, that would happen if under the worst conditions, right, of 0 vaccination rate and a very high value for D. So that's the goal, is to try to keep D down. That's what we're practicing right now, is physical distancing. And at this moment, as I make this video, I don't believe there is any vaccine yet for COVID-19. When that happens, right, then V will start to go up, and that'll serve to decrease R naught. In the meantime, what we can focus on is decreasing D. Okay. I thought that was an interesting problem in the book to talk about.